Okay, so it's 3:01. Let's get started slowly in the interest of time. Hello, everyone. Welcome to today's Athena Science webinar. I'm Ezra Bulbul. I will be chairing this session today. We have the honor of having Ciro Pinto as our speaker. Ciro is currently a staff scientist at ENAF in Palermo. He has obtained his PhD degree in astronomy working with the ULXs, and then he moved to Cambridge working with Andy Fabian, and he was an ESA fellow for a short while. Then he took his current position. His expertise is mostly in black holes and their accretion, and their feedback in massive galaxies and clusters of galaxies. Today, we will hear about his research on the fascinating field of ULXs and why Athena is the way to go. So we will hear more exciting Athena science in a minute. I will leave the floor to Ciro. Ciro?
Thank you, Ezra. The honor is all mine. So I thank you, and also Silvia for inviting me to provide a short overview on this research field, which is at the very bottom of my heart. Very quickly through the map, I just want to provide a little bit of context because this field could be interest also to those of you who work on different aspects of accretion physics, black holes, and eventually also supermassive black holes. Although the objects which I will discuss today are not supermassive black holes. They are ultraluminous X-ray sources. I will provide some information on their properties and their extrema. And I hope I can convince you that Athena is the mission to study these sources in the future. So just to keep in touch with all of you, perhaps you are all familiar with what is a stellar mass black hole. But just a quick reminder is the outcome of an explosion of a massive stars, and we can see them when they rip matter from a companion star. Then the matter doesn't go straight into the black hole. Due to rotation of the system, it forms an accretion disk, which heats up due to friction, and then it emits virtually in the entire electromagnetic spectrum, peaking in the X-rays. And the spectra, they look like a black body emission, typical of a disk emission, plus non-thermal emission from Comptonization due to the scattering of the disk photons in an optically thin corona near the black hole. These are stellar mass black holes, and X-ray binaries powered by neutron stars, they look very similar. Then we know supermassive black holes, which are the supermassive counterpart of these objects. They are located at the center of most galaxies. Spectrally speaking, they look very similar, with a dominating primary emission from the corona, which looks like a power law. In most of them, there is presence of a soft excess, but this is not the direct emission from the disk. There are the debate is still open. It could be either reprocessing or it could be a thermal blanket on top of the disk. Very often in these objects, you also have emission from fluorescence and the Compton hump due to processes near the compact object. One of the big issues with these objects is that we don't know exactly how they are born, although there are a few viable solutions, such as the direct collapse of a massive cloud of gas, merging of multiple, actually gazillions of stellar mass black holes. But of course, accretion is a very promising phenomenon because we see black hole accreting matter. The big problem is explaining how fast these objects grow, especially due to the fact that these objects are discovered when the universe was very young. As you can see from this image on the left, spectra of active galactic nuclei powered by supermassive black holes are found at very high redshift, all the way up to redshift 7 and even beyond. There are lots of recent results by JWST, which is pushing this limit even further. And that's a big problem because we need to find a way to explain how 10 to the 9, 10 to the 10 solar mass black hole can grow so fast in much less than like a giga-year, which is a very small time scale. And this is a problem also in a more generical cosmological context, because we know that supermassive black holes and their host galaxy, they kind of grow together. You know, this plot that is a well-known results for the last 20 years shows that the mass of the black hole and the mass of the bulge of the host galaxy are strongly correlated, which indicates that the two things, the black hole and the host galaxies, they are kind of growing together. And one of the evidence for the black hole to be the cause of this is the relative strength of the energy. If you, for example, measure the accretion energy of the black hole, which you see here in this equation, basically mass of the black hole times efficiency, speed of light square, and you compare to the binding energy of the galaxy, which is basically its mass times the square of the velocity dispersion, you end up finding that the energy that the black hole can release is an order of magnitude larger than the binding energy of the galaxy. And this basically is telling us that the black hole has the power to lead the growth of the galaxy itself. So it is really important to understand this, how these black holes grow, how fast they grow, and their history. Other evidence for the AGN to have a way to affect the galaxies, for example, in the comparison of the accretion history of black holes and the star formation of the local galaxies. If you see this plot here on the left, with redshift going from 10 to 3, progressively the accretion rate of the AGN increase. It achieved a level comparable to that of star formation rate, and then both of them decrease, which basically is telling us that the energy of the black hole is releasing this random medium somehow prevents for a huge amount of matter to end up again onto the black hole, as well as to form new stars in the host galaxy. So it's really important to study these objects. The problem is that these are very distant, and to study them in detail is even impossible, even with very powerful missions. So one thing to do is to search for local examples. But before going to the examples, let's take some units. You know, in the solar system, we use astronomical units. In our galaxy, we use light years. But when it comes to accretion, it's good to use the Eddington ratio. And the Eddington ratio is defined, or the Eddington luminosity limit is defined as the luminosity at which the gravitational force and the radiational force are balanced. You can work out this luminosity, which is of the order of 10 to the 38 Hertz per second, times the mass of the compact objects in solar unit. That means that for the neutron star, this luminosity limit will be of the order of 2 times 10 to the 38, and for a standard 10 solar mass black hole would be of the order of 1 to 2 10 to the 39 Hertz per second. The accretion rate can be calculated from the luminosity and would be 2 times 10 to the minus 7 solar mass per year for a black hole. You see, it's weird units with lots of exponential, so it's better to use the Eddington ratio as our standard unit. And this, of course, applies only in the spherical regime. So what kind of objects we can study in order to understand how strong high accretion, fast accretion rate works, and use them as a counterpart or alter ego for very distant active galactic nuclei? Of course, many of you might be familiar with quasars, or, for example, the high state of X-ray binaries during their outburst. They normally achieve something like 10% of the Eddington luminosity and accretion rate. But there are some objects in the local universe which go beyond that. In the case of supermassive black holes, there are narrow line Seyfert 1, a subclass of AGN, and also tidal disruption events, phenomena in which a star is ripped off by a supermassive black hole because it gets too close to it. But these are rather few, rather rare examples. And there is a problem of supermassive black holes is that their spectra peak in the ultraviolet band. So when you try to measure the bolometric luminosity, there is always a systematic uncertainty to have an estimate of the luminosity. Such uncertainty is much smaller in the case of X-ray binaries because they spectra peak in the soft X-ray where the interstellar extinction is smaller. And these objects have also smaller accretion disk. So short time variability timescales, and they provide us with further tools to study in detail the accretion physics. And this is the reason for which today we will discuss ultraluminous X-ray sources. So ultraluminous X-ray sources were discovered about 40 years ago with the Einstein Observatory, and they were empirically defined in the beginning as objects which are brighter than a 10 solar mass black hole accreting at its Eddington limit. So basically objects that are beyond the 10 to the 39 ergs per second, primarily in external galaxies, and off nuclear, so not to be confused with the central supermassive black hole. The image that you see here is a beautiful example of the cartwheel galaxy system. And there is this very interesting work by Chiara Salvaggio and Anna Volter, where they've discovered up to 37 ULXs in this couple of galaxies. So it's really an amazing factory of ULXs. The most recent catalog, I think, is the one from Don Walton, hosting up to 2,000 ULXs at distances within 500 megaparsec. And these are a couple of reviews in case you want to know some detail about these objects. Discovered 40 years ago, but as you can see from the plot here on the bottom left, the big kick in the study of these objects was when XMM Newton and Chandra was launched. This because these instruments were equipped with very powerful detectors which enable detailed studies of the astrophysics of ULXs. In the beginning, there were different channels to investigate how these objects could be very bright. I mean, we are talking of the far end high luminosity side of X-ray binaries. And of course, idea of how this could happen would be the Eddington limit simply being larger, which would imply a larger black hole mass or an intermediate mass black hole, maybe beaming due to magnetic fields or other processes which would throw most of the flux in our line of sight, which in other words means which we were overestimating their luminosity, or even super Eddington accretion. So basically vanilla black hole and neutron star accreting above their Eddington limit. And in the beginning, many people thought that we would find the missing link between stellar mass and supermassive black holes or intermediate mass black holes with masses between 100 and 100 times solar masses. There are a few examples which stick out. For example, the hyperluminous X-ray source #1 in the ESO 243 galaxy. This object is very interesting because it goes through outbursts which reminds those of galactic X-ray binaries, but achieving a luminosity of 10 to the 42 ergs per second and beyond, suggesting that the mass could be even larger than 10 to the 5 solar masses. But it's encouraging the fact that it goes between the low hard and high soft spectral state, very similar to galactic black holes, but basically with a larger mass. From the delays in the outburst, it is suggested that perhaps this was a failed tidal disruption event or a peeling event in which a star has been progressively peeled off the envelope by a massive black hole, and it's one of the strongest candidates. If you want to know more about candidates of intermediate mass black holes, there is this very interesting paper by Tanin and Webb and Natalie Webb from last year. However, in the last 10, 15 years, it became clear that there was a problem with the interpretation of Eddington limit intermediate mass black hole. One reason was the spectral shape of these sources. You can see here on the left a collection of spectra going from softer to harder, from bottom to top, of different ULXs, and the brightest among the class because they are very close to us within something like 10 megaparsec. They are very soft, way too soft if compared with the Eddington limit sources in our galaxies. But they also have a rollover around 5 to 7 keV. The spectrum goes down really sharp, which would suggest a very strong thermal emission, which doesn't really go very well with the prediction of sub-Eddington massive black holes. Spectrally speaking, they also are different in terms of continuum with galactic X-ray binaries, because as I showed you in the beginning, X-ray binary in our galaxy, which are mainly Eddington limited, they have two dominant components, the disk and the Comptonization, and sometimes you have fluorescence lines. ULX are different. They need three continuum components. A soft component with temperature below 1 keV, which could be from the outer disk, a hot thermal component, but very broad, which would suggest a rather thick disk. And then there is a hard tail, which can be seen very well using particularly the NuSTAR telescope, which goes all the way up to 80 keV. And whose origin is still not very clear. It could be either from a hot, tiny corona near the black hole, or in the case of a neutron star accretor, the magnetosphere on top of a pulsating neutron star. So one of the things people try to do is to use variability properties, and that's why these objects are better than supermassive black hole to study super Eddington or extreme accretion rates, because their variability timescales are of the order of a few days. And what you can do is to compare the luminosity of each component with its temperature and compare it to different predictions. According to theory, thin disk would be consistent with the relationship where the luminosity goes with the temperature to the fourth power. And as you can see in this very classic ULX, NGC 1313X1, the soft and the warm component are completely in disagreement with this prediction. The soft is basically consistent within different observation, while the warm one shows really weird trend, two splitted trend, each may be consistent with the prediction, but it's split in two. So you cannot model this with any thin disk prediction. And this was a work led by Dominic Walton. There was more work recently by some of our PhD students, Francesco Barra and Alessandra Robba. In particular, Alessandra found that the cool component in the source NGC 1313X2 shows a kind of inverted trend. The luminosity decrease with the temperature, which would predict an expanding envelope or even a wind to dominate the emission. And if you take the bottom of this trend to be close to the Eddington limit or the supercritical rate, which is about 2-3 times the Eddington limit, it would result in a very small mass of the compact object, so indicating a tiny black hole or even a neutron star. And you will see why this is really the case. For NGC 55, Francesco found that the trends are very close to the prediction of the thin disks, but then at high luminosity, they deviate, which would perhaps suggest that the source is crossing its critical regime and going into a critical regime where the flux is significantly affected by the presence of winds, or simply that the disk is expanding. If you assume this, that the source is crossing the Eddington limit, basically you can put constraint on the mass of the order of 10 times the mass of the sun, suggesting that the source is therefore an accreting black hole. And the same thing also would apply to Homberg too. I mean, this is a very rough approach, but it's interesting, and I think it should be investigated in the future with more observations. So it's at a very pristine and preliminary stage. Perhaps the greatest and surprising discovery in this field in the last 10 years were pulsations, where everybody was expecting these objects to be black holes of stellar or intermediate mass. Then there came a pulsation indicating that many of them are actually neutron stars. This was really surprising, and particularly when the source NGC 5907, which shine at 10 to the 41 ergs per second, was discovered to have pulsations of the order of seconds, indicating that there was a neutron star accreting at 500 times the Eddington limit, which was really a shock for the field and took all of us out of surprise. Depending on whether you assume dipolar or multipolar structure of the magnetic field, you would end up in getting magnetic fields of the order of 10 to the 14 or 10 to the 14 Gauss. The debate is still open, but I will show some more discussion. We can have more discussion about this afterwards. But what is clear is that in 20-25% of ULXs with a high quality time series, people found pulsations, which means that many of them can indeed be neutron stars. But if there are neutron stars, of course, you may also expect resonant scattering features due to the presence of magnetic fields. And this was a very difficult thing to do because ULXs are binaries which are bright, but they are at megaparsec distances. So it's very difficult to search for weak lines in their spectra, although there is some indication. One is, for example, the work done by Murray Brightman in M51 ULX08. This is not a pulsating ULX, but there is the presence of a feature at 5 keV or below, which is not consistent with any very strong atomic feature, and they interpret it as an absorption line from the magnetic fields. So depending on whether you assume this to be 2 electrons or protons, you may end up in getting completely different magnetic fields. Another evidence was found by Dominic Walton in NGC 300, and this appeared to be broad, although you can fit this feature also with other complicated continuum models. And I believe there was also a case of a cyclotron line in the galactic ultraluminous pulsar Swift J02, something like that. Now I can't remember the name. Anyway, what I'm saying is basically there are only few of them because they're very difficult to find. Right now that I'm speaking, there are around 12 neutron star powered ULX candidates, and all of them have one thing in common, and that is high spin-up rate. So many of them, the period of the spin is getting shorter, and this is really fast, perhaps due to a very strong accretion onto the contact object. There is also some further evidence of additional neutron star powered ULX to low significance pulsations, dropping the flux associated with the onset of the propeller effect and other things, but they still need to be confirmed, and we look forward to actual confirmation in the future. Again, about the timing properties of ULXs, on short timescales, there is evidence of quasi-periodic oscillations, but they are very difficult to interpret. Some people have tried to use them to obtain information on the mass, and they end up in having intermediate mass black holes predicted. But this is very difficult because also neutron stars in our galaxies have quasi-periodic oscillations. So one has to be very careful on the way it gets numbers on the mass out of this, particularly by looking at the other properties. For example, many of these sources which also have QPO, they show time lags or basically delays between the flux in the hard and the soft band. And one of the tantalizing cases is this one, AGC 55 ULX1. If one compares the light curve in the soft and the hard band, it obtains time delays of the order of a few kiloseconds. You can see here how the soft band delays the hard by that kind of order of magnitude. And this is really huge. If you associate this time delay to a reverberation, you would end up in suggesting a supermassive black hole powering a ULX, which makes no sense. So perhaps the origin in these delays is not reverberation, but it's something else due to complicated structure of the wind of the disk. On long time scales, there is evidence of superorbital periods on the order of a few months. We still don't know 100% what it is due to, but the hot interpretation is variable accretion rate, propeller effect, but highly possible the precession of a tilted disk similar to what is observed in some galactic sources, such as, for example, SS433. Regarding the donor star, so far we have only spoken about properties of the accretion disk. Let me at least share one slide on the optical emission of these objects. It is very difficult to find the donor star. Much of the emission in the optical band is due to the disk, which indeed suggests that the accretion rate is really high. But if you look in the infrared, this is much easier. And there is evidence of absorption bands, which would suggest red supergiant and in some cases blue supergiant donor stars. This is work done by different people, but in this work, I would say that the group of Peter Jonker at ESRON has done really great work in the last 10 years. So how do you end up in having this kind of objects? If you, for example, assume two main sequence stars with masses of 7.6 and 1.3, after a few thousand mega years of common envelope and stellar evolution, you may end up in powering a neutron star ULX. And actually, for a substantial amount of time, which can be of the order of 10 to the 5, 10 to the 6, the accretion rate can be even very large. What you see here is the results of theoretical work by Tauris and Podsialowski, where they show that the accretion rate can be up to 10 to the minus 5, 10 to the minus 4 solar masses per year, which for a neutron star is order of magnitude above the Eddington limit. So this is a rare situation, but it is possible, and it fits with the fact that, after all, the average number of ULX is 1, 2 per galaxy. So we don't expect this to be an extremely long period of the binary evolution. But 10 to the 5, 10 to the 6 years is still something that can be indeed detected. So super Eddington accretion, how does it work? You can imagine a massive blob of matter going onto the contact object. And what happens that the emission, it's so strong that it starts to swollen the disk to the point where in the upper region, the radiation push is stronger than the graviton pull, and therefore winds are launched. But winds are launched from something like 50-100 Rg, where the escape velocity is very large. And because of this, you would expect these super Eddington winds to achieve speeds of the order of 0.1, 0.2 speed of light. And the object would look like a massive volcanic explosion, as this beautiful bird eye simulation by Kobayashi and Ken Oshuga. Of course, the plot I showed you before applies to non-magnetized neutron stars or winds in black holes. If you have a strong magnetic field, you have to take this into account. If magnetic fields are below something like 10 to the 12, 10 to the 13 Gauss, then the magnetospheric radius would be smaller than the spherization radius where the winds are launched. And you may have something similar to what Alexander Mushtakov showed here in this plot on the left. So you may have a neutron star with strong fields and the wind as well. But if the magnetic fields are large, of the order of magnetars, then the magnetospheric radius would be so large to truncate de facto the inner disk, preventing radiation winds to be launched. So the fact that we discover or not the presence of wind in ULX may be actually an indication of the magnetic fields, or an upper limit of the magnetic field in the accreting compact objects. So I have mentioned the word winds many times so far, and you may be wondering, how about these winds? For those of you familiar with spectroscopy in general, in the X-ray, the optical or other bands, the presence of the wind can be identified thanks to atomic lines in emission or absorption, ideally blue-shifted in our line of sight by Doppler effects. And the presence of such lines is very difficult to confirm due to the distance of these objects. But there was indication for many years of spectral features around 1 keV in the CCD spectra of these objects, of ULXs. In the beginning, people thought this could be associated to emission in the star-forming region or the host galaxy. But then it soon started to be clear that the feature were variable with the spectral shape and the spectral regime of the source. As, for example, it was shown here by Matt Middleton. So these residuals vary on time scales of the order of something like a day or less, and matching the time scales of the ULX. Therefore, they have to be intrinsic to the accreting system itself. How about the high energy band in the iron K? For those of you who work on winds in AGN, particularly ultra-fast outflows, those moving at relativistic speeds, you know that the iron K band is a good way to look at winds. Also, in the slow thermal winds in X-ray binaries in our galaxy are found in this band. But for ULX, this is difficult due to many reasons. First, the objects are distant. Second, their spectra are soft, which means that there are less counts in this band. And later on, I will also show you an additional reason for which it's difficult to find iron K winds due to the ionization state of these winds. However, a few cases with very high quality data showed evidence in the iron K of blue-shifted iron K absorption lines, which would indicate the presence of an outflow. But the best way to search for winds and in general spectral feature is to do it with high-resolution X-ray spectrometers. And right now, the best ones, especially in the soft bands, are those on board XMM Newton, the reflection grating spectrometers, which are 10 times better than CCD in terms of resolution, and sometimes even better. And they have moderately good effective area. So you can absolutely detect the line, provided that you use enough exposure time, which for ULXs at few megaparsec distance, it means something beyond 100 kilosecond or so. In fact, putting data together, evidence for strong emission lines resolved in RGS spectra of ULXs were found back in 2016 by our group, but we also found absorption line by the same ions blue shifted by something like 0.2 speed of light, which would be a rock solid evidence for an outflow in these objects. Outflows that have been also discovered in other sources. Our group has done really a lot, but it is also worked by Koliopanos, Bang, and other people recently, including the paper, for example, I mentioned by Murray Brightman in the iron K band. Perhaps the best way to detect them is to perform fits with the moving Gaussian. You basically compute the improvement locally by adding a Gaussian with respect to a simple continuum fit. Then you record the chi-square, and you can calculate the single trial significance as the square root of the spectral improvement, or the delta chi-square, or the delta c-stat if you use C statistics, which in this case you should, because it's cache statistics. This was done by Peter Cosetts, our former PhD student in Cambridge, through an ESA-funded project. He searched for lines in a catalog of 19 sources, confirming that indeed the emission lines were consistent with rest frame laboratories of standard soft X-ray transition, like Lyman alpha from nitrogen 7, oxygen 8, neon 10, plus some helium triplets such as oxygen 7 and 9, while the absorption lines were found to be primarily shifted from their transition, which is what you would expect if the gas is moving in our line of sight. Then the significance was computed with Monte Carlo simulations. However, spectral fits takes a lot of time. So for this particular case, we developed a new routine that used cross-correlation between data and simulated spectra with Gaussian models rather than spectral fits, because they would take much longer. In this way, we decreased the computing time by 4 orders of magnitude, and we managed to do for many objects. Interesting result, the number of lines tend to decrease with the spectral hardness of the source, which is what you expect if you see through a funnel shape. If you see at low inclination, you can access the inner region. The spectrum is very hard, and you don't see that much through the wind because the density is very low, and the number of lines will be low. If instead you set high inclination, the inner regions are dim, and then you see through the wind, and you expect to see many lines, which is confirmed by these results. Of course, in order to perfectly identify the lines and to boost the significance by fitting more lines together, you would use more physical models, which are able to fit more lines simultaneously, models of plasma in emission and in absorption. In the case of photoionized gas, you need to take into account the spectral energy distribution. And this is the example of NGC 13x1, which is rather different from spectral energy distribution of AGN or other systems due to its high accretion rate. And this is really important to take into account, because if you compute the predicted Coulomb densities of the ion, you can see that the ions that peak in Coulomb densities are oxygen 7 and 8, while the iron K ions, they tend to have low Coulomb density, even at high log xi, or ionization parameter. And this is another explanation for the fact that we would expect most of the lines of ULXs to be in the soft band rather than the hard X-ray band. So how do we identify and search for multiple lines? We create the grids of models with different velocity in our line of sight and ionization parameter, which is kind of a proxy of the temperature. And then we scan the parameter space, searching for peaks in the spectral improvements. And then when you find a big peak, you basically find your best fit solution. And this was a great result, again, led by Peter, where we find for the first time evidence for winds in a pulsating ULXs, suggesting that the magnetic field could not be a magnetar-like. At least the dipole component could not be something like 10 to the 14 Gauss, but it should be lower than that. Winds also vary with the spectral regime. Interestingly, when the source becomes softer and bright, there is evidence for a massive component with lower velocity and lower temperature, which it's kind of unexpected given the brightness. But you know, the acid is also becoming softer. So you can imagine winds to be launched in the outer part of the disk with slower and cooler components. Interestingly, this was done also recently in a few AGN for which data was sufficient enough. We are talking of AGN accreting at or beyond the Eddington limit. And there is this very interesting work led by our PhD student, Yerong Xu, which I really recommend you to have a look at if you are interested in supermassive black holes and active galactic nuclei. So putting all the results together, can we use wind to probe properties of the accretion and the system in general? The plot that you see here on the left shows you the velocity with respect to of the wind with respect to the spectral hardness, or the relative strength of the hard component versus the soft component in the spectrum of the source. And you can see how the wind velocity increase with the spectral hardness, and the same also applies for the ionization parameters. And this is fully consistent with the funnel shape geometry, where looking at low inclination, you can see the inner region, high hardness, a very fast wind coming from the inner region, and also high temperature. Basically, would end up in this top right part of the diagram. While increasing the inclination, the wind will start to dim the hot part of the disk. The spectrum will soften. We will see through a wind from the outer region, which is expected to be cooler and slower, and we would end up in the left bottom part of this diagram. So this is very encouraging, but you can see that this is done only for 10 sources, because it's the ones where the wind is detected with sufficient significance. More recently, we have tried to use the wind to obtain information on the donor stars. After all, the wind grabs matter away from the accretion disk, which is matter that has been ripped from the donor star. So the elemental abundances in the wind should be proxy for the abundances in the companion donor star, and may tell us about its nature. For example, in the case of Holmberg 2, in a campaign led by Matt Middleton and this paper published by Francesco Barra, we were able to detect, thanks to the brightness of the source, different lines, but with a very striking nitrogen 7 line, which would suggest a highly non-solar abundance of nitrogen and a massive donor, something similar to a blue or a red supergiant. So this is something new, difficult to do because it's already difficult to detect lines. So you can even imagine how more difficult it would be to take relative ratio between lines, but it's definitely something to investigate in the future, ideally even better with more powerful detectors. Finally, regarding the winds, they can also affect the surrounding medium. In fact, if you calculate the kinetic power, you would end up in obtaining something of the order of 10 to the 39, 10 to the 40 ergs per second, which is something like 50% of the total budget. Now, it's comparable to the luminosity itself of the ULX. And this is really encouraging because it's the amount of energy that is required to inflate the superbubbles of the order of hundreds parsec that are found around many of these ULXs. So perhaps it's the wind inflating many of them, especially those which are expanding with speeds of 100 kilometers per second. So takeaway message, ULX are ideal laboratories to study extreme accretion rates and feedback on the X-ray binary scale, but you can extrapolate this also in the case of supermassive black holes. Accretion beyond Eddington is possible because only as fraction of the matter is pulled away. But these winds are important and they can probe many things. Regarding the future, it's not all gold what it glitters, in the sense that we have learned a lot, but we still don't know a lot of things. Why cyclotron lines are so rare. The origin of the time lags is not very clear. The spectral transitions have a lot of uncertainty. We don't really know the exact spectral component, what they refer to. And there are still uncertainties on the outflow rate of the winds, and especially in the launching mechanism, although radiation pressure is sufficient to explain many of the things. And the biggest reason for this is that right now, we cannot access the time scales of the spectral variations, which in many cases of the order of a day, but in some cases, it could be as short as 1 kilosecond. Many of these objects goes through flux dips of the order of hundreds of seconds or a kilosecond. And this is due to the fact that so far we have been using telescope with an effective area of the order of an A3 page format. However, we've been in a real golden era of X-ray astrophysics, thanks to many powerful missions, but the future is really bright. Now we have CRISM. Soon there might be even more powerful mission from China or NASA, but what we really look forward is Athena, and I'm going to show you why. The plot that you see here on the left is a comparison between the effective area, or basically the capability of collecting photons of high-resolution X-ray detectors on board the different facilities. CRISM was expected to significantly boost the capability of XMM Newton in Chandra beyond 1 kV, although many of you might have heard that there is an issue with the gate valve that was protecting the resolve detector that is not yet opening. At the moment, it's still closed and is kind of blinding the mission, the resolve detector below 2 kV, although JAXA will still try to make some effort to open the gate valve again. But with this in the eye, it is clear that Athena XIFU integral field unit high-resolution spectrometer will boost by over an order of magnitude and beyond our capabilities, and will be by far the best mission to study ultraluminous X-ray sources. But we really hope that somehow in the future, there will be also some complementary mission to study at higher quality the rollover of the spectrum around the 10 kV. And this could be done by either EXTP, which have very high effective area, or HEXP, which is really good in focusing capabilities. And it will do simultaneously soft and hard X-ray bands. The simulations that you see here with Athena XFU using only 20 kiloseconds unveils how a forest of emission lines will be found in this kind of sources, enabling incredibly accurate measurements of the winds, of the abundances, pulling information on the heating mechanism of the bubbles, the nature of the donor stars, and so on. For CRISM, we would expect something similar on the order, but using much longer timescales, which unfortunately cannot really probe the nature of the outflows. This is a similar plot, but using an exploration of the parameter space. And this is even more tantalizing because it shows you how we can do this with Athena only in 2 kiloseconds, which is basically very close to the shortest time scales of the variation observed in ULX sources. So this is really what we need, and this will be provided only with Athena. CRISM, okay, perhaps I can skip this at the moment. This is an interesting plot, again, on an Athena simulation done by Matteo Bacchetti to show that Athena will be able to detect pulsations of ULXs using fairly short exposures of 20, 30 kiloseconds at high significance, which means that in longer observation, we will be able to probe also how the pulsations vary. And this is really important because the pulsations are a transient phenomena in ULXs. And at the moment, we don't know why they disappear because we don't have enough quality in the detectors to study how the pulsation varies during the observation. But Athena will be able to do it. And this was a couple of plots on Lemon XP, which I can show you if you have some particular questions afterwards. But given that I think I've used all my time, I'm going to close here. Thanking you all for the attendance. If you are interested in general on super Eddington accretion and you're looking for a postdoc position, please see our CWIN website, because we have some jobs opening and you might be interesting to study this kind of physics, both in stellar mass and supermassive compact objects. And with this, I thank you all again for the attention and keep your questions.
Thank you very much, Ciro, for this excellent talk. So I would like to open the floor for questions, and I think we already have one candidate. So Mirabel, do you have a question for Ciro? Please go ahead, if so.
Yes, very nice talk. Thank you very much. Yes, the first question is some consensus on the nature of the galaxy hosts of these ULXs. In particular, for instance, the metallicity. Are these in general galaxies of low metallicity or not necessarily? And a second question is whether we know, for instance, in Cygnus X1 that there are compact jets, now relativistic jets, very well detected, of non-thermal nature. Are any relativistic jets detected in these ultraluminous X-ray sources?
Yes.
And concerning the first question is why Circinus X1, the Circinus galaxy has so many 37 ULXs. What is the speculation about this?
So thank you for the questions, which are interesting and important at the same time. For just a matter of time, I didn't show this slide, which shows the X-ray luminosity function. In other words, the number of X-ray binary at a given luminosity in each galaxy. The one that you see here on the bottom is the elliptical galaxies, where basically ULXs would end up in being the high mass end of low mass X-ray binaries, but there are only a few of them because of the age of this object. In star-forming galaxies, ULXs would therefore be associated with the high mass end of high mass X-ray binaries, and they are more frequent. So the number of ULXs certainly increase with the star formation rate of the galaxy, and therefore they tend to be found in regions where the metallicity is lower. So this was kind of weird in the beginning because, if the metallicity is low, you would expect to find a very massive black hole as the remnant of the supernova. And because of this, in the beginning, many people thought that perhaps most of ULXs were black holes, actually heavy black holes. But now we know that many of them are pulsating neutron stars. So because of this, I preferred not to include this slide because it can be a little bit misleading if one just simply look at the luminosity function. But for sure, ULXs are associated with star-forming region in the very early phases of the outburst, suggesting that they are related to a short, something like 10 to the 5 years phase of the X-ray binary evolution in the beginning of the of the system. I don't know if this answers your first question regarding Circinus X1. I don't remember exactly the type of galaxy, but I suppose perhaps it's still a kind of small mass galaxy. Is it a dwarf galaxy? I don't really remember.
Well, the Circinus galaxy, you show it, and there are 37 ULXs in the shock regions where around.
That's the cartwheel.
Yeah. Sorry. That's my mistake. I made a confusion of names. Yeah.
Yeah, but after all, even the Circinus galaxy has several ULXs. There aren't as many as the cartwheel, which is a galaxy going also some sort of interaction with the nearby galaxy. So star formation is increased by this kind of merging phenomena. But also in the Circinus galaxy, there are a few ULXs, maybe 4 or 5. Yeah. So your question was kind of related.
Okay.
And regarding the jets, yes, there are. Although it's just in a few objects, and the closest one. For example, there is a source in M31, a paper that was published by Matt Middleton back in 2013, I think. And then there was a paper by Xe on Olmberg 2. These are the two closest to ULXs. And in these ones, they found evidence for jets, of a compact jet. So the actually jets are predicted, even in the case of super Eddington accretion, but they are very difficult to search for these objects. And actually SS433, although being very dimmed in the X-rays due to obscuration, for which we only see basically reprocessed emission, it has a very strong jet, and that source is believed to be an high inclination edge on ULX. There are lots of literature suggesting this. I don't know if this answers your question.
Okay, yes, sure. Thank you very much.
Thank you.
Thank you, Mirabel. Do we have any other questions in the audience?
Somebody from Max.
Yes, Max Planck, whomever that is.
I didn't know he was still alive.
Hello, can you hear me?
Hello.
Yes.
For some reason, Zoom doesn't give my name. My name is Peter Biermann.
Hi, Peter.
Hi. And I don't know why Zoom doesn't do that. But anyway, I'm just want to comment that when you look at radio galaxy jet power, there is a minimum of this jet power, which is like 10 to the 43 ergs a second. And there's nothing below that for radio galaxy AGN. And that was shown by Pansley more than 10 years ago. And then when you look at the radio supernovae in M82 in the starburst galaxy, then you get the same magnetic field property in terms of the luminosity. So that means these black holes in M82 that power these radio supernovae are just living on spin down. And the spin down power is 10 to the 43 erg second, the same as in AGN. And that's just spin down power, nothing else. Yeah, because it has been argued by Sir Alessandro Cervi in Rome and his partners that these black holes start with very high spin. And if you then follow the spin down, it doesn't live very long because the angular momentum is gone very quickly, like less than 10 to the 5 years. But the power that you get from spin down for this short time is very, very high. It's many, many powers of 10 beyond Eddington. And that's just observations. I mean, you don't have to interpret anything. There's just radio observations that you need to do this. And so that can change the picture if you are in a very early phase of these stellar mass black holes.
Sorry, are you referring to isolated black holes?
No, I'm referring to the black holes at the center of the radio supernovae that you see in M82 and many other galaxies. And then you can infer from the data directly the spin down power of the black hole.
Yes, sorry, I have not understood if they are in X-ray, in kind of accreting binary system.
No, you only have radio data. There is no other data because of obscuration. And so in a few cases, you can use radio interferometry to get more data, and then you see that the shock wave of the supernova expands at like 0.1 C every time. And yeah, but that's radio data and interferometry, where you can see the direct expansion even at cosmological distances. And so that's all radio data I'm talking about. There's usually no other data available because of obscuration. And sometimes X-ray. We published an X-ray paper in, I think, 1985, yeah, with the early Einstein data. And no, in 19, I don't remember anymore, more than 20 years ago. And but we published the radio data in 1985. And so this is the same class of sources that you're talking about, but without all these beautiful data that you now have, and that where the sources are visible, where you only have radio data and nothing much else. And you can infer, because of the analogy to supermassive black holes, you can infer things, and the spin-down power, which Blanford-Snark emphasized already in '77, is dominant. And that is sort of the difference to your kind of argument, that the spin-down power can be really critical.
Sorry, I've not understood. Is critical to do what in particular?
Anything. I mean, if you have a spin-down power from these black holes, which is powers of 10 higher than anything else, then the spin-down power dominates, because 10 to the 43 erg independent of the mass of the black hole. And the radio data sort of give you this insight. And
I
and
see.
that is
Well,
sort
that's
of,
very, yeah, it's very interesting. I mean, some of these objects are neutron stars. So
yeah, no, I'm talking about where we don't really know for sure, but we suspect all the examples that we talk about are black holes. That's
yes,
what we
I mean,
suspect, but we're not sure.
you know, that's very interesting. I mean, if it was 10 to the 43 ergs per second, I guess we would detect them very easily in radio. So I'm not aware of any detection of something like this in classic, you know, in the standard ULXs, but it's very interesting. So I'll certainly look into that, because, but I was not aware of this. So
I mean, the data were published in 1985, and there are many more data published later. There was a big PhD in Toronto with Phil Kronberg in 1998 in APJ, and in various collaborations between Phil Kronberg and myself, we published a number of papers about this up to recently. And so that is sort of a different line of work, because we don't have the beautiful data that you have. And we tried to get X-ray data, but we did not succeed very well, because we used the early Einstein data already in the early '80s. And so they're not as beautiful as your data, but we can infer that this is basically spin-down power driven, as Blanford-Snark suspected already.
okay.
And so that can change a lot of arguments when the wind that you mentioned is actually this powerful, yeah, as you can see from the radio data.
Okay, thank you. I will absolutely look into that. I was not aware of it. Thank you.
Yeah, I can send you an email if somewhere I can find your email address.
Oh, yes. It's name, surname, @inaf.it. It's very...
Oh, I can find it through ADS, I'm sure.
Yes, absolutely.
And I'll send you an email, because we have worried about this. We discovered these radio supernovae in ME2 in 1981. And we have been wondering ever since. And
Okay.
so it's a long effort sometimes.
Sure. I agree. Thank you. Thank you very much.
Okay, thank you.
Thank you very much, Peter. Do we have any other questions from the audience? Mirabel, you seem to have your hand up still. Do you have another question?
Yes, my name is Felix Mirabel.
Sorry. Hi, Felix. Nice to meet you.
Yes. Yes, my question is, do you think, or what are the thoughts about the possibility that Athena will make a contribution to this question at very high redshifts, where are found, it is proposed that the black holes, supermassive black holes at redshifts of 6, 7, come from black hole seeds of a few thousand solar masses. And what is the contribution, if you have thought about that, of Athena to this question of how these supermassive black holes could have grown so fast? Because at some point, they must be intermediate mass black holes. And if they are in binary systems, well, they should produce what we see in the local universe, producing the ULXs. Is any thoughts about that?
Okay, good question, and very tough question. So regarding the binary systems, I'm not really sure, because supermassive black holes are always in the center of the galaxies, never outside. So if a black hole becomes intermediate because there is a lot of matter and that progressively ends up in a supermassive black hole, then I would imagine to find an intermediate mass black hole, basically somebody who didn't manage to become supermassive, who didn't get there, to still be somehow in the center of the galaxy.
So, I mean,
Can they hear you now? You have your mic.
So
Go ahead.
okay. So it's gotta be in the center of the galaxy, unless, for example, it was in a dwarf galaxy which was cannibalized, and then the black hole, due to some gravitational kick, he end up in a random place. But I don't know how frequent and how easy would be to detect a recoiling black hole in a different place of a galaxy rather than not in the center. Perhaps the ideal place to search for nowadays intermediate mass black hole would be globular clusters. And I know, there are some papers which made an effort to search for, these kind of objects, and it's kind of difficult because, of course, it's a crowded field, and the conclusions at the moment are not, I would say, rock solid, but I don't know, maybe I could be not well informed because it's not really my field of expertise. Regarding, in general, what Athena can say, it really depends on the kind of approach. One thing is how super Eddington accretion works, which in other way means can the net accretion rate surpass Eddington? And this basically would explain how fast the black hole, and even after all, if you think about the gravitational collapse of a cloud, that is by definition super Eddington. So of course, if you want the gravitational collapse to work onto something which starts small and then becomes larger, you want to make sure that you can explain that you don't throw away most of matter in excess of the Eddington limit. And in order to do this, you need to measure very accurately outflow and inflow rate, and this can be done with lots of difficulties nowadays, but with Athena you can do it very well, even in local examples. You don't need to look at redshift 10 sources. Besides, I can't imagine of a detector which would be so good to probe this object with this high accuracy that you can study their winds at redshift 10. Honestly, I don't think you can do that. And then, of course, there are other ways using, for example, JWST or similar detectors, where you search for the mass at different redshift, and then you can probe different models starting from gravitational collapse, mergers of black holes, or, for example, accretion rate. But that would be subject to degeneracy because you can't really follow the astrophysical history of an accreting black hole. So, it's one of the questions which will always be difficult to achieve, but that we asymptotically will try to get. I don't know, that is my perspective, but, I may be wrong on this, and I would be happy to be wrong.
Okay, thank you very much, Ciro. Thanks, Peter and Felix, for the discussion. It doesn't look like we have any questions anymore, no questions on Slack channel either. So let's go ahead and close this meeting for today. Thank you all very much for attending Ciro's talk, and would like to see you again at the next Athena webinar. Bye-bye.
Bye, everyone.